So let's do the same example, this time with the quadratic splines. Again, we have how many? 5 or 6? 6 data points, and 1, 2, 3, 4, 5, 6 data points, and actually you could calculate from there. And we can write 5 different, as you can see, quadratic polynomial between that. And since there are 6 data points, as we said, 5 quadratic splines passes through them. And for 0 and 10, this is the first spline equation, second, third, fourth, and fifth. And we need to find A1 to A5, B1 to B5, C1 to C5. This is the aim in here. And since we know the values there, the first thing we need to do is just plug in those values. And you will get 10 equations once you do that. And again, from the derivatives in the middle points, not the starting, not the ending point, but the middle points, 10, 15, 20, 25. That's where we are taking the derivatives, and we are using those points at the derivatives. Since they have to be continuous, we are making them equal to 0. And again, you will get 5 more equations from there. And there, if you put all those info in a matrix, this is a linear system of solution. You know that, you know how to solve it. You can just define this matrix in MATLAB, define this vector in MATLAB, and by just inverse division, you can find the result. Or you can use LU decomposition. We talked about different methods to solve it. Here is that, solving the 15 equations gives the 15 unknowns, and this is A1 to A5, B1 to B5, C1 to C5. So again, this is not easy to calculate in your hand. You need some computation power. And these are the spline equations, first one, second one, third one, fourth one, and fifth one. At T16, it is about that, so that's why we are plugged in here, and we are finding the result. And in this one, the relative error is giving us like 0.13%. And this is different technique, Lagrange interpolating polynomials. This is again a different kind of polynomial you can use for interpolating your function. And this is how we define the Lagrange interpolynomial. This is the Lagrangian coefficient and f of xi. And Lagrangian coefficient is given x minus xj, xi minus xj. When j is 0 to n, j cannot be I. So you can see what it means in here. For example, for n1, if you want a linear Lagrange interpolation, for the x0 term, there is no x0 in the numerator, and in denominator, it's coming as a difference from the x0. Similar for x1 term, there is no x1 term in numerator, it's coming as a denominator. For a quadratic Lagrange interpolation, again, for x0 term, again, as you can see, there is no x0 in the numerator, and in the denominator, it's coming as a difference for the other two variable, and similarly for the others, you can see that resemblance. And here is one example. So for the function cosine x, we are checking between 0 when x is between 0 and 1 over 2, and we are using 0 and 1 over 2 starting and ending point in that interval, and we will find the linear interpolation polynomial P1x. And since this is linear interpolation, Lagrange interpolation we are talking about, and the formula was here, f of x0 times that, f of x1 times that. That's why we need f of x0 and f of x1. x0 is 0, x1 is 1.2, and f of x0 cosine 0 is 1, cosine 1.2 is that value, and that's why 1 times x minus x1 over x0 minus x1 plus f of x1 here times x minus x0 over x1 minus x0. If you write this polynomial, here's the interpolation polynomial for you, and you can see that this is the Lagrangian interpolation for that. And the B part is asking, instead of 0 and 1.2, use 0.2 and 1. Again, instead of using the starting and ending point, we are using the points in between that. And again, the similar way, cosine 0.2, cosine 1 is given. You are just plugged in inside the formula and you will find q1x. And you can compare it which one is giving a better solution here, and you will see that q1x is a better solution. It's a better linear approximation than the p1x. And we can do the same thing for 3 nodes. This time we will be having a quadratic Lagrangian interpolation, x0, x1, x2. So what you need is f of x0, f of x1, f of x2 here, and the formula was given in there, f of x0, x minus x1, x minus x2, and denominator, it's coming difference from the x0, so that's why f of x0, x minus x1, x minus x2, x0 minus x1, x0 minus x2, f of x1, and similarly it's going like that, so that you can write the equation here. Since these are x squared terms will be coming, this is a quadratic Lagrangian equation. And for that, instead of 0, 0.6, 1.2, this time we are using 4 nodes. So we will have a cubic interpolation, which means that our the last formula will have a x cubed term. And if you will get that, you will of course getting a closer and closer results to the data set, but the computation is gonna be a little bit harder and harder. And the idea is that f of x0, x minus x1, x minus x2, x minus x3, x0 minus x1, x0 minus x2, x0 minus x3. And for f of x1, this time there will be no x1 here, and x1 is gonna be coming to denominator. F of x2, f of x3. Once you write that, you can multiply that and you will get a third order polynomial equation at that. And these are the results, the difference. This is P1, this is Q1, this is P2, quadratic one, and this is the cubic one. And as you can see, the best approximation or fitting the data is coming from the P3x, the cubic Lagrangian polynomial. This is a general way how we can define. I just wrote there because for the MATLAB part we are using this from this formula. That's why I wrote the generalization in there. Again, you don't have to understand the coding part, but you need to know how to call this function. X is a vector that contains a list of abscissas. Y is a vector that contains a list of ordinates. So what you need to do is just give the data points and you can get the Lagrangian. Okay, there. And I will give you the homework later.